Okay, so let us recall where we are. We had our fundamental theorem, and I'm not going to repeat the theorem. I'm just going to remind you what it is. So we had the fundamental theorem of statistical machine learning, and it basically said that the VC dimension determines the sample complexity of learning a class. So we have a class H, we have a notion of learning it in the realizable model, in the agnostic model, and we have a notion of uniform convergence, and we claim that all of them, this number of samples that we need, is fully determined by the parameters epsilon delta and the VC dimension. I will maybe repeat it later when we want to do concrete proofs. And so when we say that the VC dimension determines the sample complexity, it means that the VC dimension gives us both a lower bound to how many samples we need and an upper bound to how many samples we need. So last time we saw how the VC dimension provides a lower bound to the needed sample sizes. And this time we want to show how the VC dimension provides an upper bound. So we want to show that if a class has a small VC dimension, we can learn it with few samples regardless of how big the class is. Just its VC dimension is all that matters. So what we need to do today is proving upper bounds on the sample complexity, which is m pack, say, of a class H epsilon delta, just to pick one of the three quantities that we were looking at, in terms of the VC dimension of the class H. And we said that a key component in this proof is going to be a combinatorial lemma, and this is the Sauer lemma. So in order to, this is our goal, but the connection between VC dimension and sample complexity goes through this property of the Sauer lemma. So we stated the Sauer lemma. And it says that let H be a class of binary valued functions of and let the VC dimension of H be some d less than infinity, then for every m, the pi h of m is at most the sum over I goes from 0 to d of M choose I. And this, the important thing is that this can be shown to always be less than a polynomial function of M, where the exponent of the polynomial is D. So we can get kind of, I think it's always less than 2E M over D to the power D. But what we care about, I mean, we can always just approximate it by M to the D. There's then also a factor here of dividing by D that we can gain. But I don't really care about the exact number. I care about these two terms. This term just says how many behaviors can the class H have on a set of size M. The number of behaviors is at most the number of subsets of size at most D. And we will soon discuss this meaning again. And the other important statement here is this is just polynomial in M. And we have to remember what this is. This is the number of behaviors that H can have on a subset of size M. In general, if I take a subset of size M, there can be 2 to the M many 0, 1 behaviors. But we are only considering behaviors that are represented in the class H. And here it is claimed that this is going to be polynomial in the VC dimension. Yes?
What do you mean by a behavior?
Behaviors, it just means, so let us recall what this is. So we say pi H of M is the maximum over all A of size at most M of, now this is what I mean by the number of behaviors. What I look here is that I look at the size of all H intersection A such that H is in H. So I fix my set A to be a small set, and then I count how many subsets of it can H cut. This is if I view H as subsets. If I view H as functions, it's like it's the same thing. Remember we talked about this dichotomy, this duality. We can view a class of binary functions as a collection of subsets. This is written as subsets. How many subsets can H cut from A? I can also describe it in terms of functions, and I can say, we can say that this is the set. So let us just write it like this. The size, okay, this is the same as the size of all functions G that goes from A to 0, 1, such that what? So I'm looking at all the functions G from H to 0, 1, such that for some H in H, for every A in A, G of A equals H of A. Okay, so this may look even more complicated, but it's not. What am I saying here? You see, I have here my domain. I have here my domain X, and I picked some subset A. Now I have all the functions in H. So those are the functions in H. And I count how many behaviors do they have over the domain A, which is what is written here. How many functions from A to 0, 1 do we have such that some bigger function, H, that goes from all of the domain X, agrees on A with my G? Okay, so H is a class of functions on the whole domain X. Now I restricted my attention to a subset A, and I count how many 0, 1 behaviors I can get on the subset A. Okay, is it clear now?
Yeah.
Now the claim is that in general, if I take a subset A and I ask how many functions do I have to 0, 1, I'll have 2 to the m many functions. But if I only consider functions that come from a class H of finite VC dimension, I will have at most m to the d many functions. Yes?
In the chain of inequalities.
What?
In the chain of inequalities there.
Yeah.
The second from the right, is that 2e n?
Yeah.
What if d was less than 2 to the e?
Yeah, if d is less, so, right, so this only holds for m greater than 6. But that's what we care about larger numbers. Right. You're right. Because, I mean, what he noticed is that this thing could be more than 1. And then we will not have this inequality. So we just assume that this is less than 1. What do we need here? Something, yeah. At some point it kicks in, but at what point does it kick in? Oh, I need a d. I need that d is greater than 2e in order for this to hold. And then this is less than 1, and I can erase it and have less than. But I mean, this is much more easy to grasp. So I'm usually referring to this one. OK, so this is the Sauer Lemma. The Sauer Lemma claims we have only few behaviors over a set of size m. If they are all coming from a class of finite VC dimension, we want to prove it. OK, so proof of the Sauer Lemma and as I said, there are many proofs, many potential proofs. I will show you one such proof. And it's actually, we prove something stronger. So we will actually prove a stronger statement. And this is that the following claim for every H and domain subset A, the number of behaviors of H on A, right? This is what we want to bound. We want to bound the number of behaviors of H on A is bounded by the number of subsets B of A such that H shatters B. OK, so there are two things to show here. First of all, we want to show, of course, this claim. Secondly, why does this claim imply the Sauer Lemma? So, or maybe even before that, let's understand what we are saying here. Here I have a set. Here is my domain X. And here is my set A. And now I look at all the functions H, but I look at those functions as subsets. We said a function to 0, 1 is like a subset, the set of all points on which you get value 1. So H is a collection of such subsets. What do we have on this side? On this side, I look at the set A and ask how many pieces of A can we cut by putting a cookie cutter from H. So I'm asking how many pieces of A can we cut with a cookie cutter coming from H. Okay, that's the left-hand side. What is the right-hand side saying? The right-hand side is saying how many subsets of A, B are shattered by H. This looks much more demanding. A B is shattered by H if H can cut every possible subset of B. So this is counting how many subsets H can completely shatter, completely cut all pieces of them. And this is just counting how many subsets I can just get the subset. So intuitively, what looks like an easier task for H? To shatter a B or to just cut this B? What? Just to cut it. So we'll expect that this inequality will go the opposite direction. You see, this is saying how many B's I can just cut them. One H suffices to cut them off. This is asking how many B's can I completely shatter. I need 2 to the size of B many H's to shatter such a B. So for every such B, I need only 1 H. For every such a B, I need 2 to the B many H's. Intuitively, we would think that, therefore, I will cut more sets than I shatter. But we will prove that it's not the case, that it goes counterintuitively. Yes?
Are those both maxes then?
What?
Are those both maxes? Because those could have multiple values.
No, I will show it for every A. And the Sauer Lemma will follow. We'll see in a second why the Sauer Lemma follows.
But there's multiple subsets of B. Or multiple, B could be multiple subsets of A.
I don't, maybe if I don't understand the question. Maybe, can you repeat it? Okay, so this one counts how many sets of A we can cut, and this is how many subsets of A we can shatter. So let me first show you why, if we prove this claim, the Sauer Lemma follows easily. So I say that the claim implies the Sauer Lemma. Why is that? Because pi h of m, right, is just by definition, it's the maximum over all A of size m of the size of H intersection A such that H comes from H. Right? This is, by our claim, will be less than the maximum over all A of size m of what? Of the number of subsets of A such that H shatters B. Right, this is what the claim says. I can bound this number by this number. But if H has a VC dimension D, I know that it only shatters sets of size at most D. So this is less or equal the number of B's subset of A, such that the size of B is at most D. Again, maximum, max over all those A's. Right? If I shatter a B, since my VC dimension is D, B cannot have size bigger than D. Right? So this is just a number of subset of size at most D. But what is the number of subset of at most D? This is exactly the sum over I goes from 0 to D of M choose I. Because if I fix an I, M choose I is the number of subset of size I. The number of subsets of size at most d is the number of subsets of size 0 plus the number of subsets of size 1, and I sum it up to the number of subsets of size d. So this is just counts the number of subsets of size at most d. And the number of subsets of size at most d, of course, is an upper bound on what I can shatter, because I can only shatter sets of size at most d. Yes? What? Oh, what is, yeah, you cannot read it because it's my fault. Because I forgot to put here that you're all the time taking the maximum over all a's of size m. But the maximum over all a's of size m of the number of subsets of a is exactly just the number of subsets of a set of size m, whose size of every subset is at most d. So this will prove the Sauer lemma. If we could show this counterintuitive claim, the Sauer lemma will follow immediately, and we see that we see now that we really directly get the meaning of this formula. This formula tells me how many small subsets does A have. Okay, so we reduced the proof of the Sauer lemma to proving this claim. Any questions at this point? Do you want to? I guess you have the proof on your laptop. What? Oh, so yeah, no, ask me. No, I'm not blaming you. You're allowed to do whatever you do in class. Don't feel threatened. I'm not. Nothing happened. What I'm saying is that if something is unclear, I'll be happy if you ask me. I'm sorry. I'm sorry. No, I don't. What I'm saying is that I want to encourage you, if something is unclear, to ask, even if you forgot the definition. That's fine. I'm sorry. You can ask. If something is unclear, just ask, okay? I'm sorry. It's okay. I mean, if you're missing any definition, maybe other students also miss a definition. I'll be happy if you ask me and I'll repeat the definition, okay? I'm sorry that I embarrassed you. Okay, I'm sorry. But I really want you to ask. I mean, if you forget a definition, it's likely that other students also forgot the definition. Just ask. Yes. Okay, let's go on. Yeah, you've done nothing. You've done nothing bad. You shouldn't feel embarrassed or anything. Okay. Yes.
Can you explain why the size of B is less than the VC dimension?
Oh, let us recall what is the VC dimension. The VC dimension is the size of the largest set that I can shatter.
Right.
That was the definition of VC dimension.
Right.
So if the VC dimension is D, it means the largest set that I can shatter has size D.
Right.
So if I shatter a B, it cannot have size more than D.
Because it's shattered, right? Okay.
Because it's shattered, right? VC dimension was just the largest size that I can shatter.
Right.
And here I'm counting shattered sets. So they cannot have size bigger than the VC dimension.
Right.
Okay? Okay, so I want to prove this lemma, and the proof of the claim is going to be by induction on the size of A. So I want to show by induction of the on the size of A, I want to show this kind of claim, which is kind of strange claim. So if A equals 0, let's start with A of size 0. And we fix H. We fix any H and work by induction on the size of A. So if A equals 0, what is the size of the set of all H intersection A such that H is in H? Say H is not empty. How many subsets of A can I cut if A is empty? What? Oh, I mean, this is just A is 0. So the number of sets that I can cut, I can only cut the empty set because it has the empty set. So this is just the size of the set that contains only, right? It's the size of the set that contains only the empty set, which is 1. Right? And if I look at how many the collection of all B's subsets of A such that H shatters B, and again it's the same thing. H shatters only the empty set, so it has size 1. The only thing which may be confusing here is that the set that contains only the empty set has size 1. But let's accept this. It contains a set. OK. So we have the induction basis. Now we want to do the induction step. So the induction step assume the claim holds for all sets of size at most m, and prove it for A of size m plus 1. That's the induction. So let us just name the elements of A. Let A be x0 up to xm. So I have here m plus 1 many elements. And I want to count how many behaviors do I have on A. So let me maybe go back to this board. So I have my set. I have here my set A, which is of size m plus 1. And I'll just take one element, x0, and cut it out. So here I have x1 up to xm. And let's call this set A prime. So let A prime be just x1 to xm. Right? It's a subset of A. Why do I do it? Because I want to use the induction hypothesis. And the induction hypothesis, I can apply to sets of size m. So I take my set of size m plus 1, and I only consider a subset of size m. Now let us consider how many behaviors H has, we are going to consider H restricted to this set. So we will consider the behavior of H on A prime, and there we could use the induction hypothesis. So we'll define a few sets. Let's define Y0 to be the set of all H intersection A prime such that either I'm just debating between what will be clearer, to do it in terms of functions of 0, 1 vectors or in terms of subsets. And maybe it will be clearer if we do it with 0, 1 vectors. So again, what we want to count is how many behaviors, how many 0, 1 vectors I can get here. So let Y0 be the set of all vectors V in zero, 1 to the power A prime, or to the power M. So I'm looking at vectors. I'm looking at vectors that go from A prime to 0, 1, or functions that go from A prime to 0, 1. I'm really struggling with thinking of what will be the clearest. I can view it as vectors, I can view it as functions, I can view it as subsets, and I'm struggling to find what will be the clearest way to. So this, the minute I write it on the board, I realize this may be also a confusing notation, right? So, OK, let's try a third way to do it. So let's say it's the set of all G's, such that G goes from A prime to 0, 1. Yeah, that may be clearer. I look at all the functions G that goes from A prime to 0, 1, such that what happens? For some G prime, for some H in capital H, both or either H agrees with G on A prime and H of x0 is 0, or H agrees with G on A prime and H of x0 is 1. Yes?
Is that necessary? Because it's like a 0, 1 function. Won't it always either be 0 or 1?
What?
Like h of x0, won't it always be either 0 or 1?
It will always be either 0 or 1.
So this set is basically...
This set is basically the set of all H restricted to A prime. Right. So this is basically the set of all H's restricted to A prime. Right. Why do I write it like this? Because I also want to define Y1, which will be the set of all G going from A prime to 0, 1. And now I want to have the same thing, but instead of O, I will have end. So I will have such that now I'm repeating the same thing for some H in H. H agrees with g and h of x0 is 0, and for some h prime in h prime agrees with g, and h prime of x0 is 1. So this y1 is the set of all. I have this big h, and I'm looking at all the functions. Y1 is all the functions that from h on h1 on a prime that can either be extended to a 0 here or can be extended to a 1. So to have both extensions. I can extend it to a 0 and extend it to a 1. Now what we want to compare is the size of h intersection, the size. So let us, without loss of generality, let us assume, just for simplicity, that the domain of h x is just a. It will just simplify the notation. I don't care about what is happening outside A. So I'll just assume that my domain is the whole set A. OK? So now I'm claiming that the size of h, I want to compare the size of h to the size. Well, if I want to compare to the size of h to the size of, say, y0, I'm claiming something is missing here. What is missing? I'm claiming something is missing here. Here I'm counting all the functions, all the possible functions on the set A. And in y0, I'm counting all the possible functions on the set A prime. So what is missing? Yes? The functions that disagree on? OK. That's A. That's A prime. That's the whole thing is A. The smaller guy is A prime. Y0 is all the functions that I can get on A prime. And I compare them to all the functions that I can get on A. Now, for every function, if I have a function on A, I can always just ignore that and get a function on A prime. But so is it true that the number of functions on A equals the number of functions that I get on A prime? Yes?
No, because you could have a function that disagrees on x0.
Right.
y0 is slightly too big.
Right. So y0 is slightly too small. Y0 is how many behaviors do I get here? And h is all the behaviors over the whole thing. So for every function in h, its behavior on A prime will be in y0. But I could have a situation like this, that I have two functions here that disagree only on x0. But when I look at on A prime, they will look the same. In that case, I had two functions in h, but on A prime, I saw only one behavior.
So wouldn't both functions be in y0? Because y0 is the function agrees with...
Both functions will be counted only once in y0. Because in y0, I just look at how do you behave on A prime. I ask how many behaviors, this is G. G is the behavior on A prime. So if I count just behaviors on A prime, for every function h, I can have its behavior on A prime. But there could be two functions in h. H and H prime, if they differ only on this point, then they will get me the same behavior on A prime, and they will not be counted in Y0. What?
No, I understood suddenly.
Okay, that's nice. Okay, so someone understood it, which is yeah, more than my pessimistic expectation. No. Now, so what do I need to add here? I need to add something. Again, this is all the behaviors of H, and this is behaviors of H, but I only look at it from the point of view of A prime. So if two things behave the same on A prime and differ outside on X0, I will not notice the difference. So I'll count them only as one. So what do I need to add here? Yes?
Y1.
I need to add Y1. Very nice. Why do I need to add Y1? I need to add all those that I should have counted twice. Y1 is exactly all the functions in H that I should have counted twice. I have H and H prime, and they both agree with the same G. So Y prime is all the behaviors that have two extensions. If they have two extensions, then in Y0 I counted them only once. I have to count them again. So that's the main observation, that the size of H is the size of all the behaviors that I get on A prime, plus the size of all the behaviors on A prime that can be extended two ways to the new point X0. It's just if I only restrict my attention here and count how many behaviors do I have, I will miss those that have two extensions here will look like one to me, because I'm only looking at A prime. So I have to see how many have two extensions and add those, because I should count them twice and I counted them only once. So that's the main observation. Now that we understood this, we just apply the induction hypothesis to each of them. Okay, so now we are going to apply. Now we will apply our induction hypothesis to those Y0 and Y1. And why can I apply the induction hypothesis? Because note that both Y0 and Y1 are functions over A prime. And A prime is of size M. And by induction hypothesis, I know everything about size M. What I needed to show is if I know everything on size M, I can extend it to size M plus 1. So the trick was I had functions over M plus 1 points, and I described them as two sets of functions over just M points. For sets of functions over M points, I can apply the induction hypothesis. Okay? So I know that Y0, by the induction hypothesis, the size of Y0, the number of behaviors of 1, 0, is at most the number of sets B subsets of A prime such that Y0 shatters B This is the induction hypothesis. Induction hypothesis. The number of subsets, the number of behaviors on Y0 is bounded by the number of shattered sets there. And this is the same as the number of B subsets of A such that H shatters B. Now, something is missing. I mean, suddenly I'm looking at B subsets of BA instead of B subsets of A prime. What is special about subsets of A prime relative to arbitrary subsets of A, and x0 is not a member of B. Because if I'm a subset of A prime, I don't contain x0. So the size of this set is at most the size of subset of A prime that I shatter, and the subset of A prime that I shatter are those subsets that don't contain x0. Yes?
Why do you have y0 shatters B here?
What?
Why do you have y0 shatters B instead of just h shatters B?
Yeah, H shatters B and Y0 shatters B is the same thing. Because B is sitting here, B is sitting here, H counts all the behaviors over B, and Y0 counts all the behavior over this domain. So to have something in H, its behavior on B is induced by something in Y0. Yeah, so similarly, let H hat be the set of all H in H such that there exists H prime in H such that for every x in A prime, H of x equals H prime of x, but H prime of x0 is different than H of x0. So what do I count here? I count all the functions that have duplicate behavior on x0. I count all the functions that have a brother that agrees with them everywhere and doesn't agree only on x0. Yes?
Except if
What? Oh, yeah. This is not equal. Otherwise, they will be the same. OK, you got your point. So send me an email, and you get your bonus point. Yeah. Not equal, right. They disagree on it, right? And I'm claiming that y1 is just H hat restricted to A prime, right? Y1. No, I said y1. y1 was the set of all functions that have two extensions. The functions that have two extensions are the functions in H that have someone agree with them on A prime and disagree only on x0. And now we'll use the induction hypothesis for this guy. So y1 is the size of H bar restricted to A prime. This is, again, by induction hypothesis, at most the size of the set of all B subset of A prime such that H hat shatters B. But I claim, now is the next delicate, the second delicate claim, and this is that this is exactly the size of all B's subset of A such that H shatters B and x0 belongs to B. OK, so this is the last point where we have to think a little bit. Okay, so let us look at what is happening here. Yeah, it is confusing, but that will be the last confusing point. I mean, the proof is over. Just let's try to overcome this last confusing point. I have my x0 here, and I have a set here What I'm claiming is that if I can shatter this set, if I have a set B prime subset of A prime that is shattered, but every function here that shatters it also has 0 behavior here and 1 behavior here. So for every subset of B, I can cut it either with extension 0 here or with extension 1 here. But if I can cut it both with extension 0 and with extension 1, it means that I can shatter actually the set with x0. Because to shatter the set with x0, I need for every subset to have it represented in H prime. But for every subset, I can have it either with x0 or without x0. So I'm shattering the behaviors over all of this. And now we are done, because here I have, so in conclusion, this is less or equal the number of B's subset of A such that H shatters B and x0 is not in B, plus the set of all B subset of A such that H shatters B and x0 is in B. The y1 gave me all the sets that I can shatter and x0 belongs to them. y0 gave me all the sets that I can shatter and x0 is not in this set. So in conclusion, this is exactly all the shattered sets. So what I have here is at most the set of all B subsets of A such that H shatters B, which is what the claim was arguing. So we use the induction hypothesis. This is all the behavior of A0. They are at most the subsets of A0 which are shattered, which are subset without x0. And this is all the functions that have two extensions to x0. But in that case, we are shattering a set that contains x0. So in total, I can bound the size of H, the number of behaviors on A, by the number of subsets of A that the function, that the class shattered. Okay, this was the most delicate proof that we will have, I think, throughout the course. I included it just for completeness and for someone that wants to, can enjoy combinatorial arguments. I will have in the assignment 2. Assignment 2 will be, I want to upload it tomorrow or even today. It will be due in 2 weeks from Friday. And in assignment 2, I will have all the consequences of the Sauer Lemma that you need to know. So you don't need to learn this proof by heart. If you can handle assignment 2, you will see what you need to remember from this. Okay? Are there any more questions about the proof? Yes? Intuitive argument to the Sauer Lemma. Yeah, that's a hard one. Right, because this is a very non-intuitive proof. And there are other proofs I don't know if it's worthwhile. This is the proof that we have in the book. And the reason I chose it for the book is because it proves kind of a stronger claim which explains the formula very nicely. But it is not an intuitive claim, definitely. I can upload to the Learn also an alternative proof that you may find more intuitive, just for people who are interested in proofs. But it's not going to be part of the exam. Okay? So send me an email and reminder, and I'll upload a completely different proof. So, yes,
The h in the bars there
here,
is supposed to be behavior of h on A.
on A. So I had this comment that let us assume that my whole domain is A, and I'm just counting behaviors on A.
Okay. Makes sense.
Okay? Because I don't care about what is happening outside A. Yes?
So what's really counterintuitive to me is that y0 is a subset of, is a superset of y1.
Y0,
y1 is a subset of y0.
yeah, Y1 is a subset of Y0, right? So it's like you look at behaviors here. And Y0 is, you count how many behaviors here you have. And now if you want to know how many behaviors I have out of the whole set, I have to say those that have two extensions, I have to count them twice. So this is all the behaviors on A0. And these are those that I should have counted twice. So I take a subset, those that I should have counted twice, and I count them again. Every behavior on A prime either has a single extension or a double extension. So if I count all the behaviors, each is only counted once. I have to take the subset of those that have two extensions and count them a second time. Because I want to count, I want it to equal the number of total behaviors over the whole set. It is a subset. But it's a subset of those that should be counted twice. Okay? So we have the Sauer Lemma. What can we do with the Sauer Lemma? First of all, of course, we can prove the main result of the relationship between sample complexity and VC dimension. So consequences of the Sauer Lemma. We've already seen last time one of them that said the vast majority of partitions of a subset of Rn cannot be realized by a linear separator. You remember we looked at this issue of I have a collection of points, and I look at all the partitions. There are exponentially many partitions, and I ask how many of them can be cut with a straight line. And with a straight line, by the Sauer Lemma, I am bounded by pi m of half spaces. So can we only m to the power n plus 1 can be realized by cutting with half spaces, compared to 2 to the m many potential partitions of m points. OK, so that was one consequence. Second consequence is what we are going to focus on next, and this is the upper bounding the sample complexity PAC or any learning h of epsilon delta. And even before that, the Sauer Lemma also gives us a nice tool for bounding the VC dimension of complex classes. So I'll just hint in this direction, and then I'll move to the proof here. So what I'm saying is that we get here bounding, upper bounding the VC dimension of, say, combinations of, say, or more concretely, say, of H1 union H2 in terms of VC dimension H1 and VC dimension of H2. And there will be more other such combinations. So if I take the collection, I want to bound the VC dimension of the collection of all subspaces, a linear subspaces plus rectangles. So I can bound it in terms of the VC dimension of each of them by just looking at saying, so I want to show that, so assume H1 union H2 shatters some set A of size M. What it means is that the set of all H intersection A such that H comes from H1 or H comes from H2, this set must have size at least what? If the union shatters a set of size M, what can I say about this size? If I shatter a set of size M, how big should it be? Yes? At least 2 to the M. But on the other hand, this same set, the set of all H intersection A such that H comes from H1 or H comes from H2, is bounded by the set of all H intersection A such that H come from H1 plus the set of all H intersection A such that H comes from H2 I mean, this is obvious. Either it comes from here or it comes from here. But now I can use the Sauer Lemma. I can use the Sauer Lemma to say, OK, but I know how to bound this. This is at most M to the VC dimension of H1 plus M to the VC dimension of H2. And this thing is just a polynomial in M. It has to be bigger than exponential in M. This gives me an upper bound on M. M cannot be too big. And how much not too big it's going to be, that will be in the assignment. The conclusion that M cannot be too big. Because for big M, this grows exponentially. But this is just a sum of two polynomials. So for big enough M, this will be smaller than this. But if I want to shatter M, this should be bigger than 2 to the M. See, if I want to shatter a subset of size M, the number of functions should be at least 2 to the M. But by the Sauer Lemma, the number of functions that I have here is at most M to the 1 power plus M to another power. So as m grows, I cannot have that this one is bigger than this one. So I will not be able to shatter m. So the union cannot shatter sets which are too big if I have a control over the VC dimension of H1 and over the VC dimension of H2. And I leave the exact calculation to the assignment, but the idea is more important to me than the calculation. OK, so this is a very flexible tool. The Sauer Lemma, it has all kind of applications, and we want to focus on using it to upper bound the sample complexity. OK, so what do we want to bound? I want to bound, let us look at the upper bounding the sample complexity. And I want to upper bound the M uniform convergence with respect to H of epsilon delta. So let us recall what we want to bound here. So in other words, we wish to show that for sufficiently large M, depending only on epsilon delta and VC dimension of H, the probability that for every the probability that there exists H in H such that Ls of H minus Lp of H is greater than epsilon, this probability should be less than delta. And this probability is taken over all samples S coming from P to the M. This should be greater than epsilon, less than delta. OK. OK. What? But he helped. I'm running out of bonus points, but OK. I'll ask the dean for more bonus points, and I'll give both of you.
I can split it.
What?
I can split it.
I can split it. OK. OK. So, but let's go back to the topic here. This was uniform convergence. Uniform convergence was saying M uniform convergence of epsilon delta was the size that guarantees that if I take a sample of this size with high probability, for every H in H, the estimation of the loss according to the sample is not too far from the true loss of H. That allows the ERM algorithm to work.
Sorry.
Yes.
Is for every H in H, or is this just for some H in H?
The failure, the success is for every H in H.
Okay.
So I'm saying the probability of failure is the probability that some H of H fails. This is H fails. So I'm saying the probability that some H fails is small. It is like saying the probability that all H's succeed is large. Now, if we fix H, we know if we fix H, we know that the probability over samples coming from P to the M that Ls of H minus Lp of H is greater than epsilon is less than 2e to the minus m epsilon squared. That was the Hoeffding inequality. I guess you did it in the classes that Hassan taught. If I fix H, then this is just basic probability theory. If I fix H and take m samples, this is what is happening over a sample of size m. This is the true expectation. With m samples, I'm getting closer and closer to the true expectation. The probability that I'll miss it by more than epsilon goes down exponentially with the sample size.
Shouldn't you have absolute values?
There's no absolute value here. I mean, it's true. The point is that it's true even like this, right? But yeah, absolute value. But of course, if the absolute value is bounded, then also we actually need one of them. But yeah, I'm just arguing about the bonus point. It should be with, it should be with the absolute value, but it's not a mistake even the way it was written. Yeah.
Well, if you have like less than minus epsilon.
Now, we want to show that the difference in one direction is not bigger than epsilon. The difference in the other direction is not greater than epsilon. OK, so what is the see? This is like basic probability theory. I take a sample, I estimate H on the sample, and compare it to the expectation. The difference here is that I have to sum over all H's in H. And we did the connection. We went from this bound to this bound by using the union bound. So now using the union bound, over all H's in H, we got that this probability, what we really care about, this guy, that we really care about, is less than the size of H times 2e to the minus m epsilon squared. The probability of failure for a given H is this. So the probability that for some H I will fail is bounded by the sum over all H's, which is the size of H. Remember, we had this drawing. This was the set of all samples of size m. And if I pick this particular H, was the probability, the samples that make H fail. And I had to take it for every H, the samples that make H fail, to make sure that I throw away all the samples that can make, for which there exists an H that fails. The probability that a specific H fails is very small. But if I want to bound the probability that there exists a bad one, I have to sum the probability that one of them will fail, plus the probability that another one will fail, plus the probability that another one will fail. So I get this multiplicative factor here, the size of H. That was the proof that every finite H is learnable. Now we want to transition from finite H to H of finite VC dimension. The problem is that H could now be infinite. What I did here, I just repeated the argument that we had to show that every finite h is learnable. The problem is that if I sum the probability of failure of every h in h, there may now be infinitely many of them, and I'll get nothing left in my bound. It'll be completely meaningless. Now, we want to replace the size of h by the VC dimension. So the first idea will say, oh, but we don't care. Since we are only comparing the loss, we are looking at a sample. And we are comparing how many mistakes did you make on the sample. Right? What is LS of h? I ask how many mistakes did h make on the sample S. If I only care about is the behavior on the sample S, I don't care about how many h's there are in h. I only care about how many behaviors are over the sample S. So that's the main point here. I have a sample S. What is LS of h? LS of h is just looking at the sample S. And it's asking how often does h fail on S, right? What is the frequency? Now, if I have another h that has the same behavior, if I have h prime that has the same behavior on S, for me they're the same. Because if I count how often does it fail, h prime and h, if they agree on S, they will fail the same number of times. So I only care on behaviors on S. So the first idea is that rather than summing over all h's in H, we only care about behaviors of H on the sample S. And this is the number of H restricted to S such that H is in H is always finite. And it's bounded by the Sauer Lemma. So I could replace this by the number of behaviors on S. I'm finishing my time in a very bad moment, because this is the wrong proof. So I give you 2 days to think why this proof is wrong. And then we will see a correct proof. But that will be on Friday.